Okay, so we talked about the quantum mechanical model, and now we're going to look at how that can be used to explain some things that we observe. So the chemical properties of elements are periodic for a reason. It's not just a chance. They're periodic because the number of valence electrons is periodic. Elements in the same row in the column, I'm sorry, the same. Yeah, columns and rows are different things. Elements in the same columns have similar properties because elements in the same column have the same number of valence electrons. And so in a period, a row of the periodic table, we see a pattern that repeats because the number of valence electrons repeats. Yeah. So we're going to look at a few of these groups. The noble gases. The noble gases have 8 valence electrons except for helium. They're in group 8A. Helium only has 2 valence electrons because helium only has 2 electrons. The noble gases are especially non-reactive. Helium and neon are practically inert, meaning they pretty much don't react with anything. So they just do not react. They are non-reactive because they're very stable. Things react, processes happen in general to lower their energy, like balls rolling down a hill. Chemicals react to lower their potential energy. So because the noble gases already have low potential energy, they don't need to react with anything. If they react with something, it doesn't lower their potential energy, so they don't do it. So we see that atoms that have 8 valence electrons, or 2 for the little guys, are particularly stable. When a quantum level is full, like we have for neon, that second principal energy level is full. In the hotel, the second floor, all the rooms, all the beds full of electrons, that's a bonus situation. It's lower in energy. The alkali metals appear to be on the other side of the periodic table from the noble gases. And yet really, just like the Earth is not flat, and yet we look at flat maps, the periodic table isn't flat either. It's more of a cylinder. Because you should, bend it back on itself and go from neon with 10 electrons and protons to sodium with 11. And it's just really a big spiral. And so the alkali metals are really just one row to the right of the noble gases. Does that make sense? It's like, you look at a map of the world, and you see Russia on the far right side, and then you see Alaska on the far left side. And they're not like on opposite sides of the world, right? There's just a narrow strait of water between them. They're actually right next to each other. So these alkali metals have electron configurations that are very, very close to those of noble gases. They have one more electron. And they can attain a noble gas electron configuration by losing one electron. So if we look at sodium has 11 electrons, and if it loses one, it has 10. How many electrons does neon have? 10. So if sodium loses an electron to become a sodium ion, it has the same number of electrons as neon. Does it become neon? No, it doesn't. So here's where we have a high school analogy for this. So I think of the noble gases as being the in crowd in high school. That's a group of people that everybody kind of copies and wants to be like. And you kind of know you can't actually be in the group, but at least you can dress like them, right? And listen to the same music and stuff. And, humans have been doing this for generations. So the noble gases are the cool kids. The alkali metals, well, let's backtrack and flesh that out a little bit more. The nucleus is like your soul. It's who you are, right? The number of protons, the number of neutrons in a chemical reaction, that does not change. The electrons are on the outside of the atom, so that's more like your appearance, your hair color, how you styled it, what kind of clothing you wear. And so you can add or subtract electrons to an atom. So you can make it look different. So a sodium atom can lose an electron, and now the outside of it looks like neon. Same electron, number of electrons, and they'll be arranged in the same way. So sodium is, I like to personify atoms. Sodium's very motivated to do that, and will do that quite readily. So it will react with lots of things, and it'll react in a way that it loses one electron. All of these alkali metals will do that, because when they lose one electron, they get a noble gas electron configuration, and that is more stable. It's lower in energy. What they're losing is that one valence electron that they have. This gets explained later, but I'm just going to go ahead and explain it right here. Let's look at sodium. And I'm just going to draw a quick orbital diagram for sodium. So there's 1s and 2s and 2p and 3s. And sodium has 11 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So our valence electrons, this is the valence electrons right here, right? So we say, well, sodium has one valence electron. If it loses its valence electrons, so now these guys are gone. Now what are the valence electrons? Are there 0 valence electrons? No, the valence electrons are still the highest occupied principal level. So now the highest level is 2. And how many electrons are in the second level? 8. Just like the noble gases. 8 valence electrons is what everybody's trying to get. 8's kind of a magic number for electrons. That makes sense? So we can look at the group to the left of the noble gases. Fluorine, chlorine, bromine, halogens. These guys have one less electron than the noble gases. And again, they're going to react in a way to get a noble gas electron configuration, to get 8 valence electrons. So they need to gain one electron, right? I kind of overlooked a point here. That the alkali metals, come on, Pointer, you can do it. The alkali metals, the alkali metals all form +1 ions. Because when they lose one electron and form a +1 ion, then they will have a noble gas electron configuration. So the halogens will gain this is a great day. The halogens will gain an electron, and so they'll all have 1- charges. And we learned to predict these charges back in chapter 3 just by, looking at patterns in the periodic table. But quantum mechanics explains why they do this, right? They do this because by gaining one electron, fluorine can have the same number of electrons as neon. It doesn't become neon, but the electron structure is the same as neon. And that's more stable, and so it's going to do that. The halogens are also quite reactive. So the charges that we see for these predictable ions have to do with the electron configurations that are formed, and getting an electron configuration that is the same as a noble gas. So these predictable charges that we observe for these main group elements are because those charges result in noble gas electron configurations. So here is periodic table showing this, and this is now the 5th edition of the textbook, and yet the numbering in the book of these periods is still wrong. Understandable, and yet wrong, right? Because they left off hydrogen and helium because those guys are small and pesky and they break all the rules. But then you can't start at number 1, you have to start at number 2. So I corrected that, and go ahead and write in your book and fix that. Over here in group 7A, fluorine, chlorine, bromine, iodine all form -1 ions because by gaining an electron, they have the same number of electrons as a noble gas. Oxygen, sulfur, all the guys in group 6A, they need to gain 2 electrons to have the same electron configuration. So we can think of the same electron configuration, the same number of electrons as a noble gas, but really what it comes down to is 8 valence electrons.
So I know like when we first started, like we had to we would just count backwards.
Mm-hmm.
Explaining why we're counting backwards.
Yes, this is explaining why that works. Yep, exactly. And so nitrogen needs to gain 3 electrons. And I really don't understand why they always leave phosphorus off of here, because phosphorus is pretty predictable as well. Phosphorus also forms a 3- ion. And then over here, the metals, all of these group 1A metals will lose 1 electron. That gives them a +1 charge. The group 2A metals will lose 2 electrons, so they get a +2 charge. And over here's aluminum. Aluminum will lose 3 electrons. Do you notice that there aren't any predictable ions in group 4? So here, nitrogen can gain 3 electrons, or it could go the other way and lose 5, right? But losing 5 is a much bigger change than gaining 3, so it goes the closest. Group 4 is right in the middle. It would have to gain 4 or lose 4. Either way, it's too hard, and they don't. So these nonmetals up here just really don't form ions. And then these guys are just squirrely, so we didn't write them in. Any questions?
The semiconductors predictable at all?
Are the semiconductors predictable? That's a good question. The ones that are predictable, maybe use red. Oops. These guys in group 3 are pretty predictable. They're going to form +2 ions. And then we do have a couple in the transition metals that are predictable, but quantum mechanics doesn't really help us with that. And then, there's kind of a question of, well, what does a semiconductor do? Is it going to be like a metal or a non-metal? So let's look at that stair-step line. So the dividing line goes along here. And I've never seen this in print, but I've observed it to be true, that if you're looking at a semi-metal that is on the non-metal side, it tends to behave like a non-metal. And if you're looking at a semi-metal that is on the metal side, it tends to behave more like a metal. And so it is named that way and follows those conventions. But yeah, like arsenic, antimony, those guys, they don't really form ions, and the group 4s just really don't form ions either, except for tin and lead, but they're down in the bottom, they're metals, and they're kind of a different story. So,
Sorry, are the semiconductors the ones that were like this little...
the semiconductors are these guys. How could I indicate this? I'll just maybe do blue. These are the semiconductors. They're along that stair-step line, but not aluminum. Because aluminum's a metal, right? Chalkboard tray is made out of aluminum. Yeah, this triangle over here, that's just, an observation of things that only form one charge, just to help us know when to use Roman numerals and when not to. And then actually, technically, scandium over here only forms one ion as well, but when was the last time we came across scandium in a problem, right? We just don't. We just don't. So let's look at electron configurations for anions, and then we'll look at cations. So anions are formed when the nonmetal gains enough electrons to have 8 valence electrons. And what happens then is we have the S and the P sublevels are full. So sulfur, as an example, sulfur has 6 valence electrons. Here's its electron configuration. So its valence electrons right there. When sulfur becomes an anion, it gains 2 electrons, and those 2 electrons go into this last sublevel, and we end up with 3s2, 3p6. Now we have 8 valence electrons. But we also have a -2 charge, because when you gain electrons, you don't have that atom anymore, now you have an ion. So it has the same electron configuration as argon does. Everybody okay with that? Cations are formed when a metal atom loses its valence electrons. So looking at magnesium, here are the valence electrons, and I kind of got ahead of myself earlier. There's the valence electrons, there's 2 valence electrons. So magnesium will lose those 2 valence electrons, and then you might say, well, but then it doesn't have any valence electrons. Well, no, then you go down to the next layer. See, atoms have layers just like onions have layers. That was a great movie. So I think of that 3s2 as like a partial onion layer, right? And it's like, well, this is just not very nice. Let's just peel that extra bit off, and now we have a nice, smooth, intact layer of onion, right? So you peel that off, and then underneath, we have a full layer, and so this becomes the valence electrons now, and there's 8 of them. Okay? Same configuration as neon, but we've got a positive charge. Any questions? This process is always exothermic. When a cation, endothermic. I don't know where the X came from. I was like, wait a minute, that's not right. It's always endothermic. So I talk a lot about, well, magnesium wants to lose 2 electrons so that it can be like neon. Well, yeah, it does that, but there's still a cost, right? So put yourself in the place of magnesium, and it's like, well, if I got rid of these 2 extra electrons, then I'd be cool. It's a little bit like, your mom made you wear a hat to school. She wouldn't let you out of the house without the hat, right? Maybe she drove you to school, and so she's watching you get out of the car, and you've got the hat on, and you're like, man, I feel like such a dork. If I could just lose this hat, I'd look like all the cool kids, right? But you take the hat off, and there's some sort of a cost, right? Mom's going to get mad or something. You think about just losing these electrons. Those electrons belong to magnesium. He's not going to just give them to you. He's going to sell them to you. You have to give him a little bit of money, a little bit of energy for them. The cost is not very high, but there's always some price to pay to remove those electrons. I guess that's it for that section.